Hi everyone, Mr. Tong here. Now, today's video, we will be exploring this strange sensation that you get sometimes when you're taking a lift. So sometimes when you're taking a lift, you will feel like you are being pressed into the floor, or sometimes you will feel like you are floating slightly off the floor. And this usually occurs for a very short amount of time, like maybe 1 or 2 seconds. And so what we're going to do is we're going to take electronic balance and go inside a lift and do some measurements, and actually something strange happens in the measurements. Okay, so let's go to the lift and check it out. Okay, so notice what happens to the weight as we move upwards in the lift. Okay, 905 measured now. Okay, I'm going to press one of the floors and we're going to start going up and check it out. Yes, increased 961, but then after that it decreases back to 905 again. And later on, when we are nearing the top, you will notice something change as well. Oh, suddenly drops and then goes back to 905 again. Okay, so why does this happen? Okay, so first things first, we have to understand what it is that electronic balance is actually measuring. Now, if I ask you what electronic balance is supposed to measure, you will tell me it's the weight of the object that's placed on the balance. Then yeah, well, that's correct. It's supposed to measure the weight, okay? But it doesn't measure the weight directly. What it really measures is how much force you are pressing on this, and I can demonstrate this now. So this is our the scale that we were using just now, and you will see that even if I just place it like this and I squeeze the pen here, you can see that the so-called weight that is displayed is changing, right? So what it really is measuring is how much force is being applied downwards on the pen, okay? And in free body diagrams in physics, we call this the normal contact force, okay? So let's have a look at the free body diagrams in detail to see how this translates to the weight. Okay, so now let's have a look at the free body diagrams and see if this can help us to understand a little bit better how does an electronic balance show us the weight. Okay, so for this example, we're going to take an example of like this person here standing on an electronic balance inside a lift. Now, the first thing that we have to do is we have to draw separate free body diagrams for the person and the electronic scale, because these two are actually separate bodies. And so if we want to look at the forces acting on each of these bodies, then we have to separate them into two separate free body diagrams. Okay, so here we have the two separate free body diagrams. Okay, we're going to have a look at the forces on the person first. So forces on the person, I think most of you will be able to figure out, right? You have the weight of the person, which is the gravitational force exerted by the earth pulling the person down, right? So obviously the person will not be able to pass through the electronic balance, and the balance will be exerting an upward supporting force, preventing him from moving downwards, right? And this is called the normal contact force. And so these two forces, right, under non-accelerating conditions will be equal, right? Now let's have a look at the forces acting on the electronic balance. So as you know, the person is pressing down on the electronic balance, right? And so there will be a normal contact force, right, which is the force exerted by the person while he's pushing down on the balance. On top of this, you have the downwards pull of Earth's gravity, okay? So this is the weight of the electronic balance itself. And then, of course, the floor of the lift is supporting the electronic balance, preventing it from moving downwards, right? So floor exerts an upwards force on the electronic balance, and this is called the normal contact force as well. Now, it is important to note at this point in time that according to Newton's third law, there is actually one action-reaction pair here, right? So at this point, I hope you can realize, or at this point, I hope you have realized that out of these forces that we have identified here, two of them actually fall under the category of an action-reaction pair as described by Newton's third law. Okay, and they are this force here and this force here. Okay, why are they an action-reaction pair? Now, this is the normal contact force exerted by the electronic balance, right? And it's a force that is exerted on the person. This other force here is exerted by the person, right, as he is pressing down on the electronic balance. Okay, so you can see here, right, there's a certain pattern to the forces where this is a force exerted by body A on body B, and this is the same equal and opposite force exerted by body B back on body A. Okay, so this falls under the description of Newton's third law exactly. Okay, so according to Newton's third law, these two forces, right, this normal contact force here and this normal contact force here are exactly the same. Now, realize that if everything is stationary, right, if the lift is stationary, then the weight of the person must be equal to the normal contact force, right? Because the person is stationary, not accelerating. So therefore, the net force on him is 0, right? If the net force on him is 0, then weight must equal to normal contact force. And so this weight is equal to this one due to Newton's first law. And this normal contact force is an equal and opposite force to this one, right? So remember earlier we were talking about this. We were saying that on the electronic balance, right, how hard we press down will affect the reading on the scale. So you see, this is the thing here that is shown on the scale, and it is equal to this other force over here, which is indirectly equal to the weight. Okay, so what's happening here is we are indirectly measuring the weight, right, using the normal contact force exerted on the balance. Now that we had a look at the forces in detail, let's have a look at the motion of the lift. At the beginning, the lift starts off at the ground floor, and in order to move up, it has to accelerate because it's at rest. So the first part here is actually acceleration upwards. Now, we know from Newton's second law that if a body is going to accelerate, it requires something. It requires that a net force is exerted on it. And this is given by the famous equation F net equals to ma. Okay, so like say our person here, right, he has to accelerate upwards together with the lift. So how does he do this? Originally, the forces that were acting on him were balanced, right? The normal contact force upwards was equal to the weight downwards. So now, if we know that he is accelerating upwards, what does this tell us? This tells us that the upwards force must now be greater than the downwards force, right? So what the free body diagrams will look like now should be something more like this, okay, where the normal contact force is greater than the weight. Okay, this is what will give us an upwards net force, right, which will allow the person to accelerate upwards. Now, the effect of this normal contact force being greater than the weight now is going to have an effect on the amount of force that the person is pushing downwards onto the electronic balance. Okay, because these two, as you remember, are linked action-reaction pair forces. So they are always equal in magnitude, right? So if this one increases, this other part of the pair will also increase. And this is why the reading on the scale increases as we are accelerating upwards, as we have seen in the first part of the lift journey. And this similar logic will also explain what happens in the final part of the lift's journey. So you will remember from the middle part that the number displayed on the electronic balance dropped back to the usual number of 905, right? That is because in the middle section here, the lift is actually traveling at a constant speed. Okay, so if we look at the final part of the journey, the lift is decelerating as it's moving upwards. So we can say that the acceleration is directed downwards. Okay, so this is accelerate downwards. Similar logic to what we said before. In order to accelerate downwards, there must be a net force downwards. Okay, how do we get a net force downwards on this person? The weight is constant, right? Earth is going to pull down with the same amount of force. And so what actually happens is the normal contact force now decreases and decreases to a point where it is less than the weight. Okay, so upwards force small, downwards force large, so that's why we have an overall downwards net force. Now, contact force, again, this one is a action-reaction pair with this force here that is exerted downwards on the electronic balance. So if this one is now lesser than the weight, our balance will also display something lesser than the weight. Okay, so that's why you see the number on the electronic balance earlier on dropping from 905 to 800 plus, I think. So to wrap up, let's have a look at the main points that we learned in this video. First thing is that an electronic balance does not measure an object's weight directly, but rather indirectly by first measuring the normal contact force that an object is exerting on it. Okay. Second point is that the normal contact force exerted by the object on the electronic balance will be normally equal to the weight, right? As long as everything is not accelerating. But in the case of in the lift, if everything is accelerating upwards, then the normal force is actually greater than the weight. And so that's why the display on the scale will display something greater than the actual weight. And the opposite is true when there's a downwards acceleration, because then the normal contact force will be actually less than the weight. Okay, and so the electronic balance will display something slightly lower than the weight. So that's all I have for you today. Thank you very much for watching, especially if you've watched through all the way to the end. Please subscribe and leave a thumbs up if you like the video, and I will see you in the next video. Thank you.